Okay, we are recording now. Um, yeah, so I'm afraid this week, well, this last week there's been quite a bit of material covered here. So I'll go over the questions, and if you have any other questions, I'll answer them as best I can. So let me get started with exercise number 5 on the first order system. So here we are given a step input, and we are seeing that it reaches 63% of its asymptotic value of 4.25 units at time 3. So essentially, this is just a plug and chug kind of thing. We know that the first order system reaches 63% at its time constant value tau. So tau equals 3. And then we know that the when a step input, that means the amplitude of this value is 1, and we're getting a amplification factor of 4.25, so k equals 4.25. And if you plug these two in, we get the transfer function g of s is given by k over 1 plus tau s, which is over here just 4.25 over 1 plus 3s. Okay, so any questions on that? Okay, so that's pretty straightforward. Okay, so let's move on to the next one. This is also, again, just basic. These ones are mostly just making sure you know, keeping track of what the text is saying. So here we have a second order system, and we want to compute what yt is. And so for second order system, so that's the generic second order system is given by ys is k over s squared by omega n squared plus 2 zeta s over omega n plus 1. And then when it's critically damped, we know that this value is equal to 1. So that's the definition of critically damped. And so this just becomes k over s squared over omega n squared plus 2s over omega n plus 1. And if you look at this, this is basically of the form a squared plus 2ab plus b squared, where a is s over omega n and b is 1. And so this is a perfect square, k over s over omega n plus 1 squared. And so actually in the text, this is already expanded for you in terms of partial fractions. So the partial fraction expansion for this, and I believe you have access to section 811 of the text. The partial fraction you can obtain by sort of following the rules of taking the limit. And then we get the expansion of this ys is given by k over, and so 1 over s minus omega over s plus omega n square minus 1 over s plus omega n. And so what we need to do is to basically take because of the linearity of the Laplace transform, we can invert this term by term. And so when we do that, this first one is just k over s. So k over s is going to be expanded by so we get yt equals k. So the first one is just e to the minus, so k, 1 over s goes to 1. That's the inverse transform of 1 over s is 1. So that's what we get it straight away from table 5.4. And then the next one is if you take 1 plus s over omega n, this becomes minus, e to the minus omega nt, and this comes from the fact that the 1 over s plus a has the inverse transform e to the at. So s minus at, just a minute. Okay, 1 over s plus a goes to e to the minus at. So this is 1 over s plus omega n. So that's going to be e to the minus omega nt. And then for the next one, we again look at the table for the nth power decay row 6, which basically has the, if you look at that, we get the term, the inverse transform of that being omega n t e to the minus omega n t. And that's because the Laplace transform pair is 1 over s minus alpha to the n plus 1 has the time version t to the n over n factorial e to the minus alpha t ut. And because these are all systems, basically the ut is typically left out. So this is what's called often called the unilateral Laplace transform, or you can think of the ut as being given automatically because it's a real system. It's not a signal anymore. It's a real system. And so that is just a term-by-term expansion of the Laplace transform over here, gives us this value that we want over here, as we want. Okay, any questions about that? All right, okay. So moving on to the next one. So here we're saying, what's the relationship between loop gain and system fold for the proportional mode controller in example 8.9. So if you go to example 8.9, the proportional mode system. I'm just going to that right now. So this system has the following form. We are so for this system, y is given by 1 over s1 plus s tau. And so when we look at this one over here, we find that the poles of the system, which is when y goes to infinity, are for the values s equals 0 and s equals minus 1 over tau. And so the pole that we're talking about over here, and the particular pole we're looking at over here is this is the loop gain tau. Sorry, 1 over tau is the loop gain. And we're basically saying here that the system pole is at the negative of the loop gain. So pole equals minus loop gain. And so, loop gain is 1 over tau. Pole is equal to minus loop gain. So loop gain equals minus 1 over tau. And the gain is, it's not minus, it's 1 over tau. That mistake. Okay, and the reason we're saying that is that basically as tau gets smaller, we have more and more of a gain. So the time period tau sort of tells us how quickly we want to return to the set point. And so if you make that really small, then we have a very high loop gain, and we're going to return back to the we're going to try to return back to the set point very, very fast in time tau. And as tau gets longer and longer, we try to get back. It's going to take longer and longer for you to return to the set point. Okay, so any questions about this? Okay. And then going to the next one over here, then we're looking at the integral mode controls. So this is example 8.10. And what we want to do is to compute the impulse response. So the impulse response is just is basically we're giving the input of a delta t rather than the input of ut to the system. And so conveniently, the delta has a Laplace transform of 1. And so as opposed to ut, which has a Laplace transform of 1 over s. So to get the impulse response, we know that all we need to do is to take the value of the y and multiply it by 1 and then do the inverse transform. So for the second, or for the integral controller, we are given that y equals ki. The I is the proportionality for the integral controller over s squared plus ki. And so that is the form that we take because well, that's not, well, why is this r minus s over s squared plus ki w? So the we basically are going to focus on this part over here. That's the g function we're looking for. And so the impulse response for this is given by, so we can rewrite this as square root ki over s squared plus square root, oops, oh, square root ki squared. Well, it doesn't matter where the square goes. And this is because we want to make it look like a sort of in the form that looks like a over s squared plus a squared, because we know that a over s squared plus a squared has the transform of sine a, sine at. And so we put it in this form, then this just becomes the y of t is going to be given by square root ki sine of square root ki t. And so that will be the impulse response of this system when given a delta input. So what we can, physically what this means is that if we take the system and you give it a sudden shock at time 0, and then you don't give any more shock to it, then it's going to oscillate, and the oscillatory and it's going to oscillate with this period over here, square root ki t. So the time period is square root ki for the sine wave. And that's the reason why we don't really like integral mode controllers on their own, because they will oscillate. Okay, any questions about that? Okay, we're moving along pretty fast here. So okay, then the stability part. So this is the last one actually. So here the idea is to use a numerical solver to find the stability of LTI system with the denominator polynomial. So we have a system where the denominator polynomial, which means that we have some kind of a system which is a LTI system expressed as a differential equation typically, and the denominator polynomial is basically we're saying that the g of s, this transfer function, is some polynomial n of s over d of s, and you're given the denominator polynomial as this 3s to the 5 minus 4s cubed plus 7s squared plus 10s plus 1. And so there, I just used the solver that I found on the web. I can't remember where anymore, but these solvers are available. So the roots turn out to be, I guess, minus 0.108 minus 0.72 plus j 0.619 minus 0.721 minus j 0.619, and these are all fine. And then this is the problem here: 1.44 plus j 1.15, and then 1.44 minus j 1.15, and these two are in the positive half plane. And because they're in the positive half plane, the system is going to be unstable. It's as simple as that. Yeah, so that's the answer to that question. Any questions about this? Okay, so I wanted to just clarify there's a mistake in the text actually, which was about where the roots are and what happens. I just wanted to make sure I didn't make a mistake. So if you're in the negative half plane, if the roots of the denominator polynomial lie anywhere in the negative half plane, that's great, because that translates into something of the form e to the minus AT, where this is sort of, this is going to decay very fast. So that's good. If you're in the positive half plane like this, that's bad. And then if you have complex roots, they're going to be complex conjugates. So if you have any root over here, you're going to have complex conjugate, as we saw over here, 1.44 plus j 1.15, that would be this one over here, and that's this one over here. Similarly, you can have complex conjugate in a negative plane. That's okay. Now, if you have a single pair of roots on the x-axis, if you have complex conjugate that lie like this on the y-axis, like this, then that leads to oscillatory behavior. However, if you have repeated, so if you have two of them on top of each other, like so, then that's unstable. And so that's I think in one place in the text, I accidentally said that complex conjugate is repeated roots on the j-axis, on the y-axis, leads to oscillatory behavior. That's only true if it's a single pair of complex conjugate roots. If you have if you're one on top of the other, then that would be unstable. So I just wanted to make sure you got that. Okay, any questions about that? Okay, and then the last thing I want to talk about a little bit is this notion of bounded input, bounded output versus zero input stability. So the BIBO stability basically takes a system, I think I used a pile of bricks, and there's a one on top of the other, and it's lying on the ground, and we push it a little bit, and it sways, and then it settles down. So as long as the input is bounded, it's going to be, the output is bounded as well. It doesn't go crazy. But if you give it a large input, it does topple over. So that would be BIBO stable until a certain value, and then after that, so it does exhibit BIBO stability. Zero input stability says I have no input, no disturbance, but I can start with sort of an arbitrary initial state. For all values of initial state, I'm going to return to the equilibrium value. And here, I think the problem is a little bit subtle, which is what does it mean to be, what does all initial states mean? And so let's take an example like this. So let's say I have a bowl, and in this bowl, I have a marble that is sitting over here. Okay, and my equilibrium point is at the center. So one could say for zero input stability, all right, we're going to look at all arbitrary initial states. That means anywhere in the bowl, if I place it, it's going to eventually kind of settle down and kind of come down to zero. So we could say this is going to be zero input stable for all, and of course also it's also BIBO stable. If you have the thing over here and you push it, then it's going to come back over here. And in fact, it turns out to be asymptotically stable, so it does get back to the original point. But what if I have a marble on the ground outside the bowl, right? Is that a valid input state? And so it kind of becomes a matter of semantics of what is the meaning of a valid input state. So we have to define these set of input states quite carefully. In a common kind of usage, we have actual system. We say, well, this particular thing, we don't allow that. I mean, that's not in this initial state. It's not a valid state. So we have to kind of be precise in our thinking about what a valid state is. So similarly, if I had this pile of bricks over here, is a valid input state sort of bricks piled up sort of one on top of the other like that. So, and then, well, obviously this is not going to go back to here. It's just going to all fall down onto the ground, in which case the only stable situation would be all the bricks lying flat on the ground like this, right? So the definition of what's a valid input state becomes a bit crazy. So we have to be very careful. So if, some of you pointed out that one of the videos on constraints was chopped off, and that's because I had a discussion of stability there, which didn't take into account the fact what is the precise definition of a valid input state. So let's say that I have a pencil that's lying on its side. Well, this clearly is a stable system. Now, what if I put it on its on the eraser side, so and I point it up like that? Uh, is that going to be zero input stable? Is it going to be bibo stable? Well, if I get a small perturbation, it is going to remain standing on the eraser. Let's assume it does that. So you can say it's bibo stable. What about zero input stable? And here it becomes a question of what does it mean? What is a valid input state? If this is a non-equilibrium state and we'd like it to return there, well, I don't. That's not going to happen. So from that perspective, that's not zero input stable. But if I say no, the only valid input state is for it to be already standing on the edge, and all the other states are not valid states. I'm kind of making the definition. Then this is a zero input state as well. Zero input stable equilibrium as well. So it kind of hinges on the definition of what a valid state is. And so, you can, this is like discussing how many angels can dance on the head of a pin. So, you can have all sorts of answers. But in any practical system, rather than these made up examples, the system is constrained to behave in a particular way. So you're never going to have a situation where the marble kind of leaves the bowl. It's always going to be in the bowl. That's valid. And it's never going to, there's a physical, something physically prevents it from leaving the bowl. Perhaps a lid prevents the ball from leaving the bowl. And then, of course, then that state is not going to be a valid state. So one has to take into account the physical constraints in defining what a valid input state is. So anyway, that's a little bit of a thing. So when I did the example in the video that I made, I didn't go into this in enough detail, so I chopped it off. And I'm going to redo that video so that it becomes clear that there is a bit of semantics involved in it here. Okay, I'll stop with that. And if there are any questions, I can answer that now.
Hi. I had a question about the zero input. So the zero input to the system would be the command being zero, right?
That's correct. So the command is, let's put it like this. The command is what we want to achieve, and we do the input in order to achieve the command. So the command and the input are not necessarily the same thing. I mean, I think people use it a bit sloppily, but yeah, the goal is for us to obey the command essentially. And so in typical analysis, we do use the command and the input interchangeably, but strictly speaking, one has to be differentiating between the two.
Right, because like in the notes, R is taken to be zero for zero input.
That's right. So also in this case, it's also because the reference value is zero. So we like the equilibrium point to be zero.
Right.
Yeah. So that's just a convenient thing for us is if you want to get to zero. We just reset everything so that the command is zero.
And is MPC examinable?
No, I just put it in for, as I mentioned last time, I put it in because, in fact, that's how people do control these days. And well, they do that. And then more recently, people are using what's called reinforcement learning, which is a deep learning based approach. But no, it requires you to know optimization, which I don't know how many of you have had a background in optimization. So no, it's not.
Right. Thank you.
Sure, yeah. And for that matter, the videos there are made by somebody else, from somebody who's the employee of MATLAB, who I found did a very good job, actually much better than me. So that's what I'm using. Okay, any other questions? So can I ask a question now? Because I do want to get some feedback. I've been asked by the department to tell them whether I want to change the course in any way going forward. If you feel like it, I mean, you can if you just give me a little bit of feedback, any of you, about whether this is working out, whether you like it, whether I should make any changes for the next year. Noah?
Yeah, do I have any comments? I was just gonna say, actually, I might write you this in the email. Actually, I need to. I had a comment, but I forgot exactly what parts of the course were related to. So I'll have a think about the whole course, and I'll send you an email.
Okay, great. I mean, you know, I don't mean to put you all on the spot, but I know that you do course evaluations anyhow, but to the extent that you would like to help me by helping to improve the course for the next year, that would be really nice, because as I mentioned, I haven't actually done this kind of thing before, do an online course in this way, and prepare the videos and so on. So yeah, so if feedback by email, or if you want to be anonymous, I can also set up a Google form where you can, you know, fill out the form anonymously. That would be fine too. So would people prefer that? I don't know. Okay, I'm not hearing anything either. Okay, well, nobody seems to be sufficiently upset to complain about it anyway. I'll wait to hear by email, so please do that. And if you feel that you don't want to do it by email, then I'm happy to set up a Google form and get feedback that way as well. So maybe you can raise your hand if you think that the Google form is a better thing than email. Just use the raise hand button. One, okay. So only one person wants a Google form. All right, well, in that case, just send me mail, and anything is fine, you know, whatever you think would be helpful to the next batch of students taking it, which would be Lent next year, would be helpful. Okay, so just to wrap up then, we will have the office hours this Thursday. So I will be available at 10 o'clock as usual on this Zoom link. And then next Tuesday, we'll go over the last set of example questions. So I think there are 3 exercises assigned for the for simulation. And so it will just be on simulation. The NPC, I don't plan to discuss unless you have any questions or clarifications that I can have, that I can talk about. And then next Thursday will be the final assessment, and the material you already know, the post-schedule for that. So it will be on everything that's A4, L1 to A4, L4. So basically section 8.2 onwards, but not MPC until the simulation part. And then that's it. So I hope to have, I haven't actually found time to do the assessment, grading the assessments for the last week's assessment. I hope to do that today and tomorrow. So I'll be sending that feedback in the next day or two. And then the course will end on the 18th, and I'll have the assessments done certainly by the end of the month, probably a bit sooner than that. Okay, so that's that. And yeah, if there are any other questions, I can handle them now. Otherwise, we can stop. Okay, great. All right. So I will see some of you at least on Thursday, and the rest of you on Tuesday next week. Thank you. Bye-bye.
Thank you.
Thank you.